Okay, a very good afternoon, ladies and gentlemen, and welcome to our ninth and final masterclass of the year, brought to you by BEX Asia, the anchor trade exhibition of the International Built Environment Week. The 18th edition of BEX Asia happens from the 3rd to 5th of September at Sense Expo and Convention Center. So you can expect 3 days worth of sourcing from the best technology solutions for the built environment, extensive networking opportunities, and staying in the loop with the developments through our educational sessions on site. Now, before I kick off today's masterclass, my name is Suhaimi, and please allow me to go through some announcements. You should have seen some of this information about the on screen about International Built Environment Week, but do allow me to walk you through it. Now, this year's edition returns with the Expert Series, where our conference does deep dives into project case studies, best practices, and real world examples to help you develop your own expertise. Our content will cover several key domains, including on day one, digital construction, where we discuss best practices in BIM, integrated project delivery, and how it impacts the design and construction process. Construction efficiency, where we delve deep into prefabrication best practices, lean construction, and explore new technologies that will bump up the capabilities and productivity of the industry. On day two, we will deep dive into sustainability with content centered on carbon accounting and reporting throughout a building's life cycle, from construction to delivery and O&M. We will also be covering information about the mandatory energy improvement regime that kicks off in October 2025, along with retrofitting case studies around improving EUI. We will also have conversations around green mark and case studies in green building, facility management, data centers, and many more. Tickets are now available for the Expert Series. The QR code is on screen now for you, and early birds will end on the 6th of August. So do ensure that you get your tickets early so that you can enjoy the best savings available. Now, also happening as part of IBEW is the BCA Industry and Awards Dinner on day one evening, which is the 3rd of September, of course. This dinner celebrates the achievements of the industry with the pinnacle awards of the Company of the Year and Project of the Year given out by BCA, and is well attended by leading developers, contractors, and architects. So don't miss out on this exciting opportunity to meet and network with the entire value chain of the industry in one night filled with celebration, fun, and the celebration of excellence. You can scan the QR code to purchase your tickets to IBEW's Industry and Awards Dinner. And I have just been informed today that we are close to sold out on number of tables and seats. So if you're keen, please do so and register yourself by this week. Now that I'm through with sharing some of the latest updates, let's get right into today's session, proudly presented by YITEC and the Center for Environmental Sustainability. Today's topic is revolutionizing energy efficiency, cutting-edge cooling solutions for VRF systems, chilled water pumping, and data centers. And let me just talk a little bit about energy efficiency, right? I just mentioned earlier, mandatory energy improvement regime is going to kick in October this year. So this seems to be a very pertinent session for us today. And as the global population shifts toward tropical regions and climate change intensifies, optimizing energy efficiency in building operations has become crucial. And since 2006, the Center for Environmental Sustainability has been a pioneer in developing cutting-edge HVAC solutions across various industry sectors. Today's session will look at 3 key solutions arising from the work done with CFS and with YITEC around VRF, COP measurement and verification systems, distributed pumping systems, and jet impingement cooling sandbox for data centers. And I'm very pleased to be joined today by Mr. Leong Yin Chung, who is a senior manager for the Center of Environmental Sustainability, Nghi An Polytechnic. And Yin Chun has over 20 years of experience spanning electrical, electronic, and software engineering. His expertise across various diverse domains, including PLC programming, front and back-end web development, and embedded system control. With a decade of industry consultancy, Yin Chun has also developed a wide range of projects such as remote monitoring platforms of some pump systems for the Thomson East Coast Line, embedded systems for real-time VRF COP measurements, and intelligent control systems for efficient chilled water pumping. Beyond his project work, Yin Chun is passionate about knowledge sharing and is currently teaching on software quality assurance for the fintech industry. Yitek, who is also behind today's session, Masterclass, is also exhibiting at BEX Asia, booth BK15 this year from the 3rd to 5th September, so don't forget to swing by their booth. But first of all, now let me welcome Yin Chun on screen. Yin Chun, could you turn on your camera and unmute yourself? Hello, Yin Chun. How are you, man?
Yeah, great.
Okay, so tell me a little bit, because CFES is under Ngee Polytechnic, and how do you work together with YTech?
Yeah, actually, it's our clients. So ETech
Mm-hmm.
actually have some, it actually start from few years back, whereby they are actually, ETech is actually specialized in the PDV system, the passive displacement ventilation system.
Mm-hmm.
So we work on the first project whereby we look into how we can actually combine the VIF system, the air-cooled chiller, with the PDV. So that's how we start the journey. And subsequently, they're also interested, and because during that time, we are actually working on the VRF COP measurement system, and
Mm-hmm.
they're actually interested in it. And then they become our first licensee for this VRF COP system. And then subsequently, and ETEC is also the licensed distributor for the DPS, the distributed pumping system, also
Mm.
innovated from Liang Poly as well, from our side. Yeah, so that's
Right.
how we journey together until this point right now. Yeah.
Right. So this is a R&D work that is between academia and the actual industry.
Yes. Yeah.
That's great. I just love the fact that when the academia world and the industry works together, that's when you get solutions that are innovative and always fits the purpose of and the needs of the industry. Now, ladies and gentlemen, before we kick off with Yinchun's presentation, just do note that this session is slated for approximately an hour. Question and answers will be done through the Q&A function in Zoom at the bottom of your screen, and we will address any questions that you may have about the presentations at the end of the session. So, Yinchun, I shall leave it over to you. So, when you're ready, take it up.
So let me introduce myself. I'm Inchun. I'm from the Center of Environmental Sustainability, which is housed in Liang Poly. And this center is actually funded by the Enterprise Singapore, ESG. And our objective is to level up the SME and level up the industry and hope that more innovative products can be launched and commercialized in the market. Okay, some background. Liang Polytechnic, the Center of Environmental Sustainability, is trying to drive the industrial partnership for green solutions and talent development as part of the MP Sustainable Educations and Ecosystem. So right now we are trying to, because since we are innovating new stuff, right? So we are trying to work with the industry and such that we can develop some courses and we can put this newly developed knowledge back to our student, and such that when these students graduate, they will be updated with the latest technology knowledge and able to provide that kind of knowledge to the industry. And as a center, we have actually, this is our track record. We have done more than 500 consultancy projects over the past almost like 15 years. Previously, our name is called EWTCOI. It's the Environmental and Water Technology Center of Innovations. So if the people have known us for quite some time, we actually in the past it's called EWTCOI lah. Yeah, and we subsequently changed name to CFES to reflect better the nature of our work, that is environmental sustainability. So since more than past 10 decades, right, we have been work more than 500 consultancy projects. We have 70% industrial partners are SME. We have developed more than 20 know-how, and then 1 in 3 of this know-how is actually being patent licensed, IP being licensed. And then we have a multidisciplinary team and more than 15 laboratory and workshops. So actually, we welcome all kinds of different industry that come to us if they have a problem statement, and we can also introduce to our colleague in the school if those domain area doesn't fall exactly in the environmental sustainability as well. Yeah. So when you talk about environmental sustainability, we actually have 3 teams here. One is the water team. The second one is the sustainable materials, and the third one is energy efficiency. And definitely for me, right, actually from the energy efficiency team, and definitely we also have colleagues from the water and the material team as well, whereby we try to develop something that's sustainable for the industry. All right. Let's go into the main three technology that I want to introduce to everyone today. This is the innovations that whereby we already license off. Definitely have more innovations whereby we are developing right now. But this is the three technology that we already have successfully launched in the market, and then it's already quite successfully commercialized. Yeah, and the first one is the VRF COP measurements. Just like I've mentioned that we work with EDEC and they already licensed off. And surprisingly, the first client is actually Daikin and Mitsubishi. They actually want to know what is the efficiency of their system. So let me introduce what is all this about. Yeah. So why should we measure VRF COP, the efficiency for the VRF system? The first one is definitely because all these VRF system, right? They could be installed. You can chuck any places like in the corners. You can see in these photos here, whereby the VRF system is actually installed is in this location, whereby the hot air probably can short circuit because of the low ceiling. And then we have probably there's another problem is that you have a long pipe length to the FCU, and there's a poor equipment maintenance. For example, in this photo here, you can see the fin is already quite badly damaged, whereby the efficiency for the heat transfer will be quite bad. And definitely another problem is oversizing, because basically in the industry, the consultant probably will use the rule of thumb to estimate what should be the cooling load of the buildings, and they probably oversize. And people simply don't complain if overcool, and people will just complain if it's too hot, right? Yeah. And another problem is the stack effect. Yeah, it's actually, you can see in this particular photo here, whereby the VRF is actually installed in a high-rise building, and the hot air will basically just rise up, and if the VRF on the top of the building, right, probably we have all the hot air, and the ventilation will be quite bad in this case. So because of all these reasons, right, the VRF may not be performing as what is stated in the catalog. And as you know that the catalog probably, actually I know that from Daikin and Mitsubishi, they actually tested and obtained all those COP value from a factory tested environment. So it's like in a controlled environment, they test the machines and produce those catalog value. But if you install this VRF system that is on site, then the problem will be, as what I mentioned, is all these problems here that might affect the VRF COP value, the efficiency value. And definitely, if you want to improve the energy efficiency, you have to do the measurement first. Yeah, and actually, when I come across that right now, AI is very hot topic. All the artificial intelligence, they mentions like, oh, I have this AI here that actually can help you to improve the efficiency for air cons, regardless is chiller plant or VRF. So actually, to me, I'm quite surprised when you can't even measure the efficiency of the VRF, how to actually able to optimize it. And definitely, I've heard many solutions like, oh, you have this occupancy sensor, whereby if there's no people there, probably you can switch off the air cons or all kind of that kind of solutions. But to me, right, if you have occupancy sensor to switch off the air cons, it probably just automations. Yeah, it's not really it's not really optimizing the efficiency of the aircon yet. And definitely, if you can't measure the efficiency, you can't really optimize it as well. And then, and since Green Mark 2021, we start to see there's some actions from BCA, the Building and Construction Authority, that they want to look at the VRF COP as well. And then in this clause, right, actually they required to measure the VRF system up to plus minus 10% accuracy. And even if there's a VRF supplier in-house monitoring system, for example, like Daikin and Mitsubishi, if they have their own system that can reflect their own system COP, all these systems need to be certified with a plus or verified with a plus minus 10% uncertainty as well. So this actually is a problem statement that's from the Green Mark 2021. And then in 2024, this Green Mark 2021 is actually put into actions. And that's why you actually can see this in the Green Mark right now, that they are asking for the total energy efficiency of 1 kilowatt per ton. And then for this VRF system, they're asking for 0.78 kilowatt per ton, which is equivalent to a COP 4.5 in this case. All right, so that's why that is the incentive, the motivation behind why we want to create this system here. whereby this system is the first non-intrusive system. It can do a real-time measurement as well, and we actually work with A-STAR, the National Meteorology Center, to verify if our system actually can meet the plus minus 10% accuracy. So how do we do it? This is just a very simple layout to show the very simple schematic to show you how this system works. Basically, it's very similar to a chiller plant whereby we have to measure the temperature of the supply and the return temperature, and we measure the flow rate. Similarly, in this case, for the refrigerants, we actually measure not just the temperature but also the pressure. So from the temperature and pressure, we are able to tell what is the enthalpy or the energy per kilogram of the refrigerant that is running between the condenser and the indoor evaporator. And we are using an ultrasound flow meter to measure the flow rate of the refrigerants. Yeah, so it's very similar to the chiller plant way of measuring the efficiency. The challenge in this case is that because ultrasound flow meter in this case only can measure volume flow rate, but in this case we need mass flow rate. And that's why we have the program there. We actually built in a controller to collect all the data, and we calculate what is the density of the refrigerant at real time based on the pressure and the temperature. And definitely we also key in all the thermodynamic tables inside our controller to do these real-time measurements. So this is our prototype that is a few years back. We have the pressure gauge here. We have the current clamp to measure the power. This is the data logger with the touchscreen display with the power meter here. This is the ADAM. Basically, it's an analog to digital converter to convert all the temperature and the 4 to 20 milliamp to our controller. And then we have an ultrasound flow meter here as well. So basically, that's how we do the measurements. And definitely, they have a controller that's hidden behind this board here that do all the magic. Yeah. And definitely, if we have the measurements, actually just one step further, that will have the cloud system. So we also built in the cloud system for EDEC that we can measure. Now we can actually measure what is the COP value of the on-site VIF system, and the end user can actually log into the portal and see what is the COP value online at real time. So these verifications that we work with the ESA, so you can see that the efficiency of variable refrigerant flow system were evaluated to be within 9% for the it's a non-intrusive system. So we don't need to cut the pipe, we just have the ultrasound tap on it, and then we can tell the COP at real time. All right, and this is the actual on-site installations. So this is a pressure gauge here, and we just install the pressure gauge via the service port, and such that it's still non-intrusive in this case. And this is an ultrasound flow meter. It's a very small ultrasound flow meter probe that we can measure the flow rate on a very small refrigerant pipe. And then this is the actual deployment. We have all the control panel here to see the value. And because of this technology that we developed, we actually have enough inquiry from our industrial, whereby they import some of these energy efficient products from overseas. And then they are actually asking us if we can verify if those products can actually help to improve the COP of the VIF system. So you can see these products here, this extra fin here, and then we have this solar panel as well, solar panel here to see whether there's any improvement. And recently, we actually worked with our client on this spray cooling as well. We are trying to spray water on the condenser coil to see if there's any improvement also. Okay, so that's the first technology on the VIF COP measurements. On the second one, after tackling the VIF measurement, right, the next part, we're actually working on the chill water for chill water system. And let me introduce, actually this is a project they work with Grundfos, the pump maker, the world's largest pump maker. And let me go through this video, and probably you can understand a bit better on what is the distributed pumping system.
There are many considerations when designing a cooling system for commercial buildings. To cool a building, existing chilled water systems generally use large centralized pumps and chillers in the mechanical room for pushing water around the chilled water loops. Regulating the flow due to the varying cooling needs is traditionally done using balancing and control valves, typically located close to the terminal units. But even efficient valves consume unnecessary energy due to pressure losses. Furthermore, a bypass line is typically used in the system to ensure sufficient flow to the chillers. Cooling systems with central pumps and valves have been designed in this way for decades. However, there are issues shared by existing cooling systems that lead to high energy consumption and less comfort in the building. One is commissioning and balancing, which is traditionally a time-consuming and tedious procedure, but essential for ensuring a system that operates to its highest potential. Inadequate commissioning leads to poorly balanced systems and excessive energy use. An incorrectly balanced system will result in having terminal units receiving more or less flow than necessary. This could also lead to low delta T. This is especially apparent at part load conditions and results in less comfort. But what if we design the system in a better way? Our solution is Grundfos distributed pumping. By replacing valves with intelligent pumps, we use less energy while bringing more intelligence to your cooling system. A Grundfos distributed pumping system uses the maintenance-free Magna 3 circulator and low-pressure non-return valves to prevent backflow. The distributed pumps ensure optimum pressure and flow at each terminal unit at all times. This also allows the centralized pumps managed by a new control logic to be significantly downsized because of the distributed pumps. This new design delivers perfect cooling comfort when and where it is needed within the building. With Grundfos distributed pumping, you achieve the following benefits: an automatically balanced system at any load, significant energy savings, easy and fast commissioning. Let us help you design an efficient and reliable system with our knowledge and advanced tools. Cool your building more intelligently with less energy. Grundfos distributed pumping.
All right, so that's the Grundfos distributed pumping system. Okay, so back to our from the video. And this distributed pumping system actually started almost in 2017 or 2018, around that period, whereby Grundfos have a problem statement asking if there's any way that their smart pump can be used in a bigger way. And then our team actually think about it, and we actually introduced this distributed pumping system to the Grundfos team to see whether is that bigger picture, that bigger applications that we can actually put the smart pumps inside the buildings. And that's how we start our journey. And the first building to introduce to materialize or implement this distributed pumping system is actually a Grundfos headquarters in Jalan Tukang. And subsequently, that's actually a two-story factory buildings. And then subsequently, with the success, we actually now put the system at the second building is at our Ngee Polytechnic, Block 22, which is, you can see from this picture here. It's a building that with a canteen, with a study area, with office and a sports hall. So during the exam period, this sports hall will be full, and we have a full load in that case. And during the term break, we have no student, or basically the canteen with totally empty. So you can see that this particular building will have a very high variations in the heat load, and then this is a very good building to test out whether the distributed pumping system can actually cater for different kind of load, even at part load conditions. Okay, let me go through what is the traditional way of doing the pumping. Basically, it's a primary only pumping system, whereby you have a primary pump that trying to pump the water to each of the branch or each of the air handling unit. And then if let's say if a particular branch that require less cooling, for example, the modulating valve will start to close the valve to limit the amount of chill water going inside. That's how you control the temperature for the air handling unit. And definitely, for the balancing valve, you need the balancing valve. The reason is because just imagine if all the balancing valve is fully open, definitely most of the water will go to the nearest branch, and there will be less water go to the furthest branch. And that's why before you can control the amount of water into each branch, you will need the balancing valve to make sure that there will balance of water in each of the flow, in each of the balance flow in each of the branch, and subsequently then you can control with a balancing valve. So now with this system here, you can see there's a problem of you have a huge pressure drop. On one side of the public pump, you're trying to push the water, and the other side, you are trying to stop the water. So that's how that's why the energy is being lost in this case. And then in our system, what we do is that we actually remove all the valve, and then we add a pump, a secondary pump for each branch of the ASU. And because the Grundfos smart pump actually have all the temperature sensor and the VSD built in, each of these branch here will become their own control loop. So they actually independently control the temperature within the loop here. Yeah. And with all the flow that is combined, we actually also downsize our public pump, and we control our public pump according to how much water that's required in the secondary loop. So in this case, we have instead of a bypass, we have a decoupler, and our control strategy is to make sure there's no flow in the bypass, and such that how much you pump at the primary side will be what's required in the secondary side. So there's no over pumping, and there's no under pumping as well. So that's how we manage to reduce the energy that's required to pump the water in this case, because we basically remove all the valve. All right, so this is the actual implementations. You can see that in this particular block in Neon, block 22, during the implementations, we actually remove all the modulating valve. We also remove the balancing valve in this case. It's a bold move. Imagine this is operating buildings, and as we have of course, we have done many simulations before we do our job to make sure that we have enough confidence to really retrofit the building in this way. And then we have the smart pump as well. So we put in the smart pump to replace the location of the valve. So it's actually very nicely done. And you can see that this pump is quite small, so we don't need much support. We can just have an inline pump that is joined on the pipe, along the pipe itself. And for the public pump, you can see that in this picture here, this is the existing 5.6 kilowatt pump. And then with the Grundfos pump that we install in line, we actually just reduced to 4 set of 1.5 kilowatt from 4 set of 5.6. So you can see this is after retrofitting. You can see it's very beautifully done, I would say. It's all in line, and then and actually this pump is actually very small as well, and also because the existing pump location is here, that's why we have still put the pump. Put the line here and put the pump in the middle. Otherwise, this small pump can probably go at the top there and just go direct actually. And this is the result. We actually collect the data on the exam week, whereby it's a full load conditions. We also do the data collections during the teaching week and the term break as well. So actually we collect the data for the whole year. So we do a 1 year of data collection for the baseline, and then after retrofit, we do another 1 year of data collections after the retrofit to make sure that we actually cover all kind of season in Singapore, even though it's always summer. Yeah. So in this case, during the exam week, we actually see there's reductions of the pumping energy, reductions of 44%, and there's a reductions of the volume of chill water pump, reduced by 28%, and there's a reductions of operating cooling capacity as well, 8%, and there's an improvement for the delta T, and the reductions in the kilowatt per ton up to 40%, and that's the exam week, whereby it's the full load conditions. And this teaching week, similarly, we see a 33% reductions in the pumping energy, 80% in the chill water pump, reduction of 21% on the cooling capacity, and then there's an improvement of the delta T 1.4 degree, and reductions of 16% on the kilowatt per ton for the pumping. And finally, for the break week, whereby it's a low load conditions, that's where we see a much bigger saving. You can see the pumping energy, there's a reductions of the 67%, and the reduction of the average pumping kilowatt per ton up to 59% in this case. So it's a great reductions in the energy. So this is a summary. We actually licensed this to Grundfos, and this technology is already well adopted in the regional market in Malaysia, Thailand, and Vietnam. If I remember correctly, right, the Shopee data center in Thailand is actually using the distributed pumping system right now, and there's a reduction of commissions time of up to 80%. Actually, just we have seen the video whereby you will need to do the balancing for the traditional system. But for this, because it's the individual control loop and they won't affect the other branches as well, the pump will just modulate itself to pump the exact amount of water to the ASU, and that's why you can see there's a huge reductions in the commissioning time. The ROI is 3 years for existing building and 6 months for new buildings. And this is summary. Basically, we managed to save up to energy saving up to pump energy of 55%, chiller 12%, and a chiller plant altogether will be 17% in this case. So this will be my last technology that I want to introduce. That's the data center cooling. So let me go through how the data center cool right now traditionally. In Singapore, mostly we are still doing the air cool system, whereby we have a crack unit. Basically, crack unit is an aircon. Basically, try to pump the cold air to the raised floor, and you have a rack, many rack of server that's lying on the data center floor. And if let's say if someone is using this particular rack, the damper in front of the rack will open to allow the cold air to come out, and there's a lot of fan inside the rack that will suck in the cold air to cool down the server. And after the cool air go through the server, become a hot air or the warm air, it will go through the hot aisle and go back to the crack unit to cool down. And this is basically it's just an aircon, right? So with the aircon, definitely you need the chiller, you need the cooling tower. Basically, it's whole set of the aircon system that you need to support the air cool system for data center. Now, the problem is right now, as you know, we have a lot of AI, we have a lot of GPU, whereby it's already well known that air cool will not be efficient enough to able to take out the heat for those GPU system. And then definitely you also have a challenge to distribute the air equally. And just imagine if there's this huge data hall, right? You have all these rack, and you can imagine the data rack that's at the furthest end probably would have less air, because most of the air would just go through on the first nearest rack, right? And even if you balance the rack properly, balance all this damper properly, most of the cold air probably will still go to the bottom rack, right? Because as the air go out, it will be less air at the top to go in to cool the server at the top side. Yeah, and definitely because you're using fan, you have a high fan noise. Yeah, in this case, and definitely this is a second type of technology. There's immersion cooling that's very popular right now as well. It already exists in the market for almost more than a decade as well. The problem is all this coolant, this is how it works. Let me introduce how it works first. Basically, you're trying to submerge the entire server into this liquid tank here, whereby the liquid is not water, it's like some kind of coolants, dielectric coolant to cool down the server. So now the problem is the coolant definitely is very expensive, and you have a weight limit on the floor loading. That's definitely for Singapore, you have high-rise building of the data center, and you probably will look at this way is a multi-story kind of swimming pool in this case if you are using this kind of technology. And you have lesser server per floor area because you can only work on the human height level. It's unlike the air cool server, whereby you can actually stack up the server, right? But in this case, because of the maintenance issue, you can only do on the human height level. And you have a greater loss of coolant liquid due to evaporation during maintenance. Definitely, you have two types of liquid coolants. That's a popular one. The first one is the oil-based, and the second one is a two-phase liquid. For the two-phase liquid, basically, if you open the tank like this, it will start evaporating. But even if you are using an oil base, you have to clean the oil during the maintenance. Just imagine if you are doing maintenance in this case, right? You need a crane to hoist up the motherboard and wait for the oil to drip before you can do any maintenance. So that is the problems. That's the issue that's using this kind of air immersion cooling. And only like recently, we have this new technology that's called the cold plate. So basically, as you can see from the diagram, you have basically the heat sink with a water tube that's going through the heat sink to cool down the chip that is below it. Yeah. So the problem is that you have a risk of water leakage. That's number one. And then the second part is that probably it's not everywhere on the motherboard will be cool unless you want to cover everywhere with the heat sink lah. Yeah. And based on the chip size, you might need to customize this heat sink, the location as well. And the challenge is the water distributions for the small tube. Just imagine, look at this diagram here. On just one motherboard, you have so many water tube here. And with the pump that's pumping in the water, how to make sure that the water will be evenly distributed on each of these heat sink. And just imagine, let's say on the furthest end here, maybe it's here, there's one important chip here, one IC chip that's below here. And definitely you don't have a flow meter to tell whether there's enough water going through the heat sink here. And then let's say if this particular chip might overheat. Here might have a lot of water here, the nearer one, and the further one might have no water and it will burn out in the end. You have no idea, basically. Yeah, so that's the challenge of using this kind of cold plate system. Yep. So with all the existing system, so let me introduce our system here. It's called the jet impingement data server cooling. So this is our prototype. So you can see how it works. Basically, instead of submerging the entire motherboard, we are just doing a showering. We shower the motherboard with a spray plate. So how it works is basically we actually design this spray plate here and we place next to the motherboard. So as the system starts, it will start to spray the coolants on the motherboard evenly everywhere on the motherboard itself. So with this system, basically the good point is that we drastically reduce the amount of coolant that's needed. So in this picture here, right, just imagine if for the immersion cooling, basically you have to submerge the entire motherboard up to this height here. But what we need is basically for this system, because we are just spraying, we only need this small amount of coolant at the sump here, at this reservoir here, to circulate the coolant to cool it down. So as the coolant heat up, because it actually taken out the heat from the motherboard, all this coolant will be warmed up, and we actually send this coolant through a heat exchanger, which is at the bottom here. And the other side of the heat exchanger basically is the cooling water. So we just use the cooling water to cool down the coolant, and the coolant will just circulate inside this chassis inside here. All right. Okay, so we have this technology whereby we work with Hypercool and EMS, and this technology is already patented. And compared to air-cooled system, we managed to have a 90% saving as compared to air-cooled system. And we achieved low PUE of 1.07, and right now we have improved further. We have already managed to reach 1.04 for the PUE. There's in case let me introduce the PUE. Basically, it's the power utility effectiveness. What it means is that for this 1.07, for example, right, what it means is that for 1 kilowatt of the IT power for the server load, we only use 70 watt of energy for the cooling. And for the standard right now, as advised by IMDA, the standard is actually 1.3. That means 1 kilowatt of IT load, we use 300 watt to cool it down. But now we actually just use 70 watt. And right now, as I mentioned, we just managed to use 40 watt of energy to cool down. Yeah. So actually, we designed this system based on the standard 1U size, the 1U server size, and we actually can put this back to the standard air-cooled server right here. All right, so this is just now you can see it's just a prototype as we show from the video, and this is the actual system that we already built, and these are actual products. And then you can see that the number of water pipe that is going in and out is only 2 per server. And definitely right now we are actually working with our client to see is any way to do a 5-in-1. You can see from this picture here, this is a 5-in-1 system. So there's only one water in and one water out, and there's a heat exchanger inside this compartment here that spray the coolant that's inside for all the 5 servers inside. Yeah. So there's this system here, and you can see that this particular door here, we design it as a door, and for the maintenance, it's actually much simpler, whereby the people can just open this door here, slide out the motherboard inside, and then do the maintenance and slide it back and close the door. And so this is how easily you can do the maintenance. And definitely for the performance, we have tested it for almost 6 months, more than 6 months already. We actually launched this data sandbox here last June. So right now it's already, yes, actually more than a year plus. We have been testing it, running it at 100% load. And we actually can maintain, okay, this is 100% load, and we able to maintain the temperature below 60 degrees. And definitely because we are using a pump to circulate the coolant, basically we can actually even further lower down the temperature, but definitely the energy will be higher in this case. We will need more pump energy to circulate the coolant. But definitely we can right now can control much better control on the temperature. So we adjust around like below 60 degrees, and then that's our benchmark in this case. Yeah. So for the cooling water side, we use the distributed pumping idea, whereby we use the Grundfos pump to distribute the water. This is the schematic. So you can imagine if there's many of these server rack, we can just use a distributed pumping idea to how to distribute the cooling water to each branch of the server rack in this case. And for the water, definitely, we mentioned about the cooling water, right, that take out the heat from the coolant. The water can just send to the air cooler and able to cool down by the ambient air. Okay, so this is even a bigger design for the whole floor. And for this data server here, in this particular room of the data center sandbox, we actually put this in a study area, whereby in this study area, we actually have another technology, and thanks for EDAC, actually they are the one that we work together with the PDV. So you can see that it's basically we're using a natural air ventilations, whereby the warm air will go up and the cold air will come down to cool down this room. So this is a high efficiency, there's no fan, that's why it's very efficient kind of aircon systems. And then even with this energy saving, energy efficient air conditioning system, we are able to cool down the server in this case. Yeah, and definitely we put in our own technology for the monitoring for the any intruders into these locations here. All right, and this is why we actually want to put this inside the room, is because we want to show that we don't need a special area whereby, for a typical servers data center, you need a raised floor, you need a crack unit, you need the chiller, you need the cooling tower, and so on. But we are demonstrating in this case that even for a normal study area, we are able to put the server here, and the heat will take care by itself within the system itself, and there's no noise also. And that's why we can put in this study area, whereby a student right now actually putting here, whereby a student will be able to sitting around here, and they can connect to a server to do the AI training. That's the purpose why we put here lah. Yeah. So this definitely we also put inside our cloud system. And in this particular schematic, you can see that we have achieved a PUE of 1.06. It's actually real-time measurement at this moment. And I just take a screenshot at this particular operations time. And you can see that for the 4 server here running, we actually send the cooling water to a fan that's outside, and we just control the fan. And you can see the fan speed running is just 20%. And the PUE is 1.06, yeah. And we have the cooling water back to the server to take out the heat from the coolants. So you can see that for this particular example, we don't need any chiller, we don't need any cooling tower, and so it's just a dry cooler, a fan to cool down the cooling water, and it can just continuously running. So that's all for my technology. So in this particular slide, I just want to introduce how we can partner together with SME to work together on innovative projects. So these are different kind of model of collaborations. We can do a contract research, we can do a tech consultancy, We have other essential service like testing for membrane, that's for the other team and so on. We have facility use because we have many advanced measurement tools, that's for the chemical side. Yeah. So we also welcome facility use to rent our machines, and definitely we also provide training courses. And recently, this is one of the examples that I want to introduce. There's the Go 25 that is already on the news. These are very good examples of how we actually work with authority and the SME as well, to how we come with innovations to do some things for the initiative, different kind of initiative for the authority. So for this example, right, it's a Goal 25, whereby the agency, the authority actually try to encourage the building owner to set the aircon set point to 25 degree, and they would want to know how this will actually affect the occupants' comfort level and what's the reductions in the energy. So in this particular project, we actually put in our new innovations. There's a human comfort controller, whereby we measures the temperature, humidity, air velocity, and even the radiant heat to see, and we calculate this particular human comfort index called the PMV, the predicted mean vote, to tell how comfortable is the people inside the aircon space. And we actually work with the SME, the people that's in the industry, to able to give us the permissions to do this experiment in a real operating environments. So this is the partnerships. We have a lot of partners from overseas, from local as well, and definitely we will hope that your company will can engage us for this kind of projects, for consultancy project as well. All right, so that's all I have. Yep. Thank you.
All right, thank you, Yin Chun. And ladies and gentlemen, once again, if you have any questions for the Q&A, please do drop them in the Q&A function using the Q&A function at the bottom of your Zoom screen. I'd also like to now invite to join us for Q&A Patiwata Pochum so that he can address some of the more technical questions. I see we already have a number of questions already submitted by our audience, as well as some questions that came in during registrations. But while we wait for, let me just, something went wrong with my video again. Yes. So while we wait for further questions to come in, let me just take some of the questions from the registrations time when people had submitted their registrations. Yeah. But first of all, I think when for Yin Chun, when you said about the distributed pump technology, that I found that really interesting. I think that, do you think that there will be a lot more applications for it, especially in smaller office buildings, given that, the load and occupancy in buildings is now fluctuating a lot more because of work from home and people not having to be in the office every day?
Yeah, sure. I think the merit of this, the great advantage of this system is to tackle the low load conditions. I'm not talking about the chiller side, definitely, because I'm talking about the pumping side in this case. So for the traditional system, because if let's say, especially if the valve, and the problem with the valve is that it's something called the valve authority as well. What it means is that sometimes you open the valve fully, you don't have water. Sometimes when you have the valve open a little bit, you have a lot of water. So this is the problem during the control, especially during the commissioning time, whereby if you don't do it properly, you have a lot of problem in the future as well. And because of this, during low load conditions especially, you may not be able to control it to the fine detail. And sometimes, especially for the public pump, you also cannot ramp down so much. Yeah, but for this smart pump here, because Grundfos, they actually cater for this small flow rate applications, and that's why they are able to actually give a smaller flow rate for a particular branch in this case. And now we can able to control the water in a very step manner, I would say, because basically if there's the particular branch don't want water, they will pump less or basically shut down the pump. And in this case, we can actually tune the step. I mean, I have a lot of steps in this case to cater for different kind of flow that's required.
Right.
Yeah.
Okay, so let's start taking questions again from the audience. I think the first question, I think this came up during the point when we were talking about the green mark standards. What does it mean by 10% uncertainty? The installed instrumentation must have the capability to calculate the resultant system efficiency within 10% uncertainty. Are you able to address that, or should we?
Yeah. Actually, as what I understand, I've been going through this procedure with the BCA. I've been followed up quite closely. Originally, from almost like 10 years ago, right? I think when the Green Mark just launched, they just give points to the chiller plant. Right? The reason is because basically very simple. VRF cannot produce a COP value, very hard to measure, and that's why at that point of time they only give points to the chiller plant. And subsequently, because of this, right, Daikin and Mitsubishi actually engaged us to look into possibility of real-time measurements for the VRF. Yeah. And subsequently, definitely the guideline, the government guideline, the authority guideline, will have to follow up with the stage of the technology. So as we start to do this research and we manage to get this value for the COP for the VRF, and now the Green Mark actually introduced this guideline to say that even for VRF, probably you also need to do the measurements to have the points. Yeah. And definitely in Singapore, there's actually many buildings that have this VRF system for their buildings. And this Green Mark actually is not talking about all kind of building as well. It's only for building that's more than 2,000 square meter. If 2,000 square meter you're using VRF, then you have to probably need to do the measurement in this case. Yeah. Now the problem is if let's say definitely because of our engagement with Daikin and Mitsubishi, right now their own system, if you purchase the system, right, and you pay some subscription fee, the system will be able to produce a COP value through the high level, through the BATnet or through Modbus. It's actually BATnet lah. So through the high level, you can actually grab the COP value. Now, definitely now the challenge will be each of the manufacturer definitely will claim the COP is good, right? Now, who can tell the system is actually have a bias of plus 0.5, plus 1? No one can tell, right? So now definitely there must be some accuracy value. Even for chiller measurements, you have the heat balance and so on to tell where's the uncertainty in the measurement, right? So for this VRF as well, if you produce a value, you must have an uncertainty behind it as well. If let's say if the uncertainty is 50%, that means you are tikam lah, right? No point lah, right? So definitely that's why right now the BCA actually putting down this clause to say that it's recommend to have this plus minus 10% for your value that is produced from your system. It can be from our system because we work with A-Star that we already certified to be plus minus 10%. It's already licensed to ETEC, and that's why ETEC also providing the services to many buildings owner right now to measure the VRF COP. And definitely if you don't want to engage ETEC, you can also engage Daikin and Mitsubishi also. But the question is if the system is within the plus minus 10%. That is the unknown at the moment. Yeah.
Right. So obviously that sort of answers the next question is the report that you generate can actually be used for submission for Green Mark points.
Yeah, definitely. Right now, we have actually worked through one project whereby I think I better not to disclose the address and the brand, but we actually through ETEC, and then we actually produce the report. We do the ETEC do the measurements, we collect the data, and we actually written some of the report, and then we submit this to the ESCO, and then the ESCO is preparing the Green Mark, the documentation for submissions.
Another question that came from the audience, which you slightly addressed earlier in your answers, what is the deviation of your measurement versus VRF in-house supplier measurement usually on your COP from your experience? Sensitive question, huh?
Yeah, it's a very sensitive question. You're right. Actually, we have signed various disclosure, non-disclosure agreement with Daikin and Mitsubishi and with LG as well. So definitely there's some difference in the measurement methods lah. Yeah. So but definitely I think I better not disclose, but I can, as you can see my side, how we do it is basically we have an ultrasonic flow meter, and I mean you can open up the the Daikin, Mitsubishi, or LG system can open up their system to see there's ultrasound flow meter inside or there's any flow meter inside. Definitely, I don't think don't have lah. I think it's quite well known. Yeah.
But I think it's also important that the COP is also not just to note that what they publish is in laboratory settings.
Yep.
And of course, how you use the systems and how they are installed, will also make the difference, right? You mentioned, for example, if you stack them too much, then obviously it affects the COPs for the systems at the higher tiers. Another question here, can your distributed pumping system be used for malls with a lot of FCUs instead of AHUs?
Yes, correct.
Around,
It's also possible.
it's
Yes, can be
possible.
done. We have done project that we have FCU as well. So is see how we design it lah. Definitely, if you have more pumps, definitely the cost will go up. And definitely, if let's say if the FCU is a very small size, it's also like not really economical to have a pump for individual FCU. So in this case, we have done project before whereby we have a valve. We still use valve for the FCU. But on top of the valve, right, we are still using a distributed pumping. Yeah, so it's a mix of the valve and the distributed pumping system.
Okay. It seems that there's a couple of questions here asking how they can get in touch with you because they want to do research and cooperation with you. Do not worry, ladies and gentlemen. If you want to know more, do send your question. Do not make it anonymous because we will then be able to follow up with you separately on this. Let's move on to a couple more questions, which is on now the distributed pumping. When you mentioned about the distributed pumping that you use ground force technology, what redundancy do you have in place in the event that a pump fails? Because per line you have one pump, right?
Yep. I think I'm not the best guy to do this because you can ask Grundfos how do they do it. But what I understand is that they have this pump. There's a twins head with a twins head basically is two so you can see there's a backup there. So even you have one pump, then you can actually buy the twins head kind of pump, and then if one fail, the other one will actually being a backup. You can also program the twins head pump, right, to run 50-50 also possible. So there's a different configuration for Grundfos line of products. You can actually consult Grundfos, they can give you a solution. And actually, right now, we are actually working in Ngee Ann that we are trying to retrofit one of the building and we also trying to get this twin head pump in the event of redundancy. Yeah.
Right. I guess for particularly if you're talking about data centers, redundancy is super important.
Yes.
Extremely important. Now, the other question here is, how did you manage to stretch the delta T by 2 degrees Celsius? Did you change the room temperature set points? Did you increase the room temperature set point?
No, we are actually trying to do the before and after as equal as possible. But definitely, being an operating building, it will be quite challenging lah. Yeah. But we try to have the set point. We actually work with our PMS system, the facility management people in Ngee Ann, to ensure that most of the time the set point is always the same. So how the delta T is being better control, this is something that we are trying to investigate at the moment. Yeah, because there's a lot of change in the dynamics inside the system, the hydraulic and everything else that would change the efficiency as well. For example, right now, as you can see my slide previously, we actually have reductions in the cooling load also. This is actually very surprising to us because if talk about when we first present this data, right, this result, right, people will start to ask, is it because no people, that's why the cooling load is lower? How come the cooling load could be lower? So that is the question we face, and definitely, but somehow when we work with many different type of buildings, we also see a similar kind of observations. And one of the reasons now we suspect, we are actually working a project with Grundfos, it's an ongoing project to investigate this actually. And what we are looking into is possible because of the valve, the efficiency of the valve control. Yeah, because when probably we will take it for granted the valve will actually do its job. But the thing is that when we look closer, most of the time, the PID, especially the PID, the proportional integral controller, the derivative, the PI controller, to control the valve, right? Most of the time you have a lot of fluctuations. You have a lot of up and down, overshoot, undershoot, overshoot, undershoot. And sometimes you have a large steady state error in the end. That means actually most of the time, while the people feel comfortable, they don't have complaint, but it's actually never meet the set point. The reason is because the valve never control properly. And that's the reason when you're using a pump whereby you can meet the set point closer in a much better, efficient manner, then now we can actually have that saving. Probably it's not a saving, but I would say it's a better in control to meet the set point in this case. Another thinking is that just imagine just now we mentioned about the valve authority, right? The thing is that the valve opening don't give you flow. Okay, so it's more or less indirect. It's indirect. It depends on the pressure in the pipe, how much pressure and how much opening that will give you the flow, right? Now, this is indirect. This control is indirect, okay? But for the pump is basically give you the flow. It's direct control in this case. So you can see the control is much more direct and much more efficient. And I would say it's much easier to control the flow in this case. Yeah.
That's true. Well, ladies and gentlemen, it's 4:33, so that's about all the time that we have today. So thank you very much for your attention and joining us here at the final masterclass of BEX Asia, presented to you by YTech and the Center for Environmental Sustainability, both of whom will be at BEX Asia from the 3rd to 5th of September. If you've not registered, go to the website bex-asia.com and register yourself. Attendance at BEX Asia is free. And of course, if you want to find out more about energy efficiency and retrofitting solutions case studies, that's where you go to IBEW and get your tickets here before the early bird expires. So that's about all that time you have here today. So thank you very much to Ying Chun for answering the questions and sharing the work that you've done in R&D and testing them in the real world basis. Ying Chun, any last words for our audience here today?
Yep. Please drop down your name and your company name, and if you have any problem, just come to us. We always welcome all kind of problem statement from the industry, and we always love to see the actual problem in the industry and how we can actually work together to solve it together.
Sounds great. So those, I just saw another one. Hi, can I also have your contact details? Don't worry, as I said, we know, because if you didn't send it as an anonymous, we'll have your email addresses and we'll be sending them over to Ying Chun and his guys at CFES, and you will be able to be in touch and come up with your own problem statements and hopefully find a better solution to make the world a better place for all of us. Ladies and gentlemen, thank you very much, and I'll see you at BEX Asia, 3rd to 5th of September at Marina Bay Sands, Singapore. Have a great week ahead. Bye-bye. Thank you, Yunchen.
Thank you.